So we study how to generate digital twins of real-world elastic objects. So for example, we create a digital double of this car sponge, capturing both the geometry and nonlinear elastic properties. So our solution is to poke the real object with a force meter and a laser to measure contact forces and indentations, and then we use this data to optimize a 3D elastic nonlinear material that matches this acquired data. And our materials are stable and suitable for computer animation use, and these objects that you see now were made out of the captured foam materials.
We present the diffusion probabilistic model for audio-driven group choreography synthesis. Given a base of music, our model generates the whole group dance animation sequence from a random noise distribution. We further introduce a contrastive learning objective to enable controllability of the generated animation. Our model can create high-fidelity group dance animations with different consistency or diversity level from only a single music. We can also synthesize group dance with flexible number of dancers, or even long-term choreography animation while maintaining the coherency among dancers. Thank you.
See you at our session. Thank you.
To add physics plausibility of human motions, we introduced GroundLink, which is a 3D mocap dataset with ground reaction force and center pressure that distinguishes individual feet. The force data is synchronized with kinematics data. We captured our data in our biomechanics lab with 20 high-speed cameras and 5 force platforms for high temporal resolution. We also introduced GroundLinkNet, a benchmark neural network model we trained with GroundLink. It predicts the ground reaction forces and center pressures from pure kinematics. We demonstrate some prediction results from external mocap data.
Thank you.
Neural inverse kinematics is the task of recovering a full pose from sparse constraints. Current neural IK are not pose-aware and hence lose any progress made using traditional posing tools. Our model that we call SCALE-IK is conditioned on a base pose and can preserve this progress. Using our model, we can perform fast neural posing, provide multiple suggestions for the same constraint configuration, and by using a motion sequence as a series of base poses, we can even perform motion editing. To learn more, come join our talk on Thursday morning. Thank you.
I'm moving my hand inside the water. Look, the same water flow is replicated in the simulation. Let me explain how I do this. With some motion tracking wizardry, we collect flow data using buoys. The motion data of the buoys alone is enough for the replication. And this is me messing with the water in real time. Here's a fun fact. When some people first see the video, they think the left-hand side looks like floating cigarettes. I repeat, floating cigarettes. I don't know what you think, but I'm convinced. See you on Thursday.
To reconstruct controllable 3D head avatars from monocular videos, current methods train dynamic neural fields conditioned on expression and pose. However, neural fields can be slow to render, even on high-end GPUs. Can we render our head avatar much faster? Yes. To achieve this, our work bakes train neural fields into deformable multi-layer meshes plus a lightweight neural network. With our baked representation, dynamic head avatars can be easily rendered on mobile devices in real time. Our method not only achieves better visual quality compared to existing methods, but also has a rendering speed that is about 100 times faster. To find out more, come to our talk.
Thank you.
We pre-process track meshes to position maps, which together with average textures serve as our network inputs. Through a VAE architecture, our network outputs personalized head avatars. In order to achieve more precise control and be more photorealistic, we prefer a representation called surface-guided neural points. To be more efficient, we work in 3 aspects: fewer shading points, faster per point decoding, and faster training speed. Here, we show some talking head demos.
Approach your interview with statuesque composure.
Thank you.
Introducing Avatar Studio, a text-guided editing approach for dynamic full-head avatars.
We move beyond traditional controls and provide genuine, personalized edits through text. Leveraging state-of-the-art dynamic neural radiance fields and a combination of text-to-image diffusion models, Avatar Studio crafts photorealistic avatars. We introduce view and time-aware score distillation sampling, which allows seamless and view-consistent editing.
Dumpy keep beats, jingles, next checker, overflow.
For more fun avatars, please visit our talk.
We present any portrait guide, a method that can generate diverse 3D human portraits with controllable camera viewpoints, facial expressions, head pose, and shoulder movements, and it is trained on unstructured 2D image collections. Our method is based on the generative radiance manifold representation and equipped with learned deformation fields. Several novel modules are proposed to achieve controllable and high-quality generation. For more technical details and results, please refer to our paper and project page.
Given a realistic portrait, Nerface lighting regoverns a 3D reconstruction for it and predicts the corresponding studio albedo for relighting. Given a reference lighting condition, Nerface lighting is able to produce consistent and real-time 3D relighting results while supporting free manipulation. Here shows more results of 3D-aware relighting of Nerface lighting. Thank you.
3D reconstruction and AI-generated models offer alternatives to manual artistry. Reducing texture storage is crucial. Based on the analysis of repetitive content present in model textures, we propose an automatic pipeline to reduce texture size. The input is a 3D model with a texture and a UV map. Our method detects and removes repetitive features, compresses the background texture, creates a new UV atlas, and bake a new texture. We tested this on 3D scanned model datasets, achieving a high texture compression rate and maintains excellent visual quality. We use our method to compress the texture of each model. More visual contrast is shown here.
Thank you.
We develop a number of modifications to differentiable rendering that make it suitable for texture baking arbitrary models. Our additions fully preserve the appearance of the original, even with few polygons. This is in contrast to prior work, which cannot recover sharp details in some models, blurring regions with geometric differences. This is fixed by two new techniques during differentiable rendering. By jointly optimizing a parallax mapping, geometric differences are mitigated, and by optimizing UV layout, higher frequency detail is kept. We test our approach on 30 different models at 3 levels of detail and show our approach outperforms prior work and industry tools for texture breaking at all levels. Thank you. Please come to our talk on Thursday.
Closed architecture models are often generated from 3D dense reconstructions for downstream applications. How to create realistic textures for such an abstracted proxy with tons of high-resolution images remains open. We present TwinText, a fully automatic texture mapping framework to achieve this. See the visual comparison of two challenging cases against commercial software reality capture, state-of-the-art texture mapping method, and ours. Look at the photo-level texture generated with our TwinText. Please come and check how we do that on Thursday. Thank you.
HyperDreamer supports high-fidelity 3D generation, and it also predicts BRDF materials and environment lights, enabling realistic rendering results under different lightings. Then, let's start editing now. We propose an intelligent and user-friendly interactive 3D editing tool. Firstly, users can segment any region of a 3D object by one-shot selection. Then we can efficiently edit the texture with text-based guidance to modify the targeted region, enhancing the editability and flexibility of the HyperDreamer.
Thank you. We present a hybrid explicit-implicit representation for text-guided 3D shape generation.
The explicit stage controls the topology of the generated 3D shapes and enables local modifications, whereas the implicit stage refines the shape and paints it with plausible colors. Our hybrid 3D shape representation, namely EXIM, combining the strengths of explicit and implicit representations. Beyond existing works, we achieve high-fidelity shape generation from natural language descriptions. Further, we demonstrate the applicability of our approach to generate indoor scenes with consistent styles using text-induced 3D shapes.
Motion graphics are animated graphic designs used to catch a viewer's attention. They are commonly found in digital advertising, logos and branding, film and TV title sequences, and all across the web. But they are primarily available as video, which makes editing them very difficult. We've built a pair of tools to address this challenge. Our motion vectorization pipeline converts an input video to an SVG motion program that explicitly represents the objects and their motions. With our Program Transformation API, we can programmatically edit the motion programs and generate a new variation of the motion graphic, or many new complex variations.
Thank you.
Are you tired of generating pixel images or finite resolutions? Well, good news, we developed a model to create vector icons that can scale to any size. Given text input, our method can create high-quality icons of different categories. There are many different applications. First, you can modify an icon with a text input. You don't need to use professional tools. Second, when you are creating your own icons, our method can predict the next possible path for you, greatly improving your efficiency. Come check it out.
Recently, diffusion models have become popular in text-to-image generation. However, the image generated in JPG or PNG formats are hard to edit. So we present a novel pipeline that, given the exemplar SVG and textual prompts, our method can generate high-quality customized SVG. These SVGs preserve layer-wise path properties and are very easy to edit. For more details, welcome to our paper session. Thank you.
Our model takes a shape image and a prompt describing an object as input and generates an artistic glyph image consisting of such objects, which we call innovative artistic fonts. Our approach is unique in that it can preserve the object's original shape while constraining its position, and our training method requires only a small quantity of generated data, making it an efficient, unsupervised learning approach. Experimental results demonstrate that our method can generate various glyphs, including Chinese, English, Japanese, and symbols, using different objects.
Thank you. Lithography systems are important for printing the semiconductor chips and optical devices. But how to digitalize a lithography system? So previous methods usually use the white box method. They do with analytical equations. But we do in a gray box manner. We use process data to boost the performance of the system. And we also demonstrate our work in downstream tasks, such as camera design and HLE design. We show we have improvement performance in both holography tasks and computational imaging tasks. Please come to see our talk on Thursday. Thank you.
In this paper, we challenge to reconstruct transparent objects in nature scenes with only the multi-view images as input. Just using mobile phone, common user can finish all setups in several minutes, and then reconstruct the object with fine structure. And welcome to our talk for more details.
We introduce Shader, an example-based deep generative model that produces high-resolution 3D texture geometry through shape detailization and differentiable rendering. Given a coarse voxel and a textured style shape, Shader first generates 3D geometry via multi-resolution shape detailization. then synthesizes 3D volumetric textures via differentiable rendering. Shader is capable of generating high-resolution 3D novel shapes with better geometric details and clean textures. The modeling interface powered by Shader allows users to edit the coarse content voxel model and visualize the detailed texture shape interactively.
Please come to our talk on Thursday morning. Thank you.
We present Dr. Occluder, a novel course-defined framework for occluder generation. The occluder uses very few faces to maintain similar occlusion properties of the original 3D model. With the occluders, we can achieve occlusion culling with much lower computational cost and latency. Our method inputs a 3D model and outputs a triangle set. We first project the model to obtain silhouette images and use a trained convolution network to produce vertex offsets. These offsets deform distributed triangles into a preliminary occluder, and we refine the occluder through differentiable rendering. Compared with state-of-the-art technology, our occluders can occlude much more area with the same number of faces.
Thank you.
Various scene representations have access to differentiable rendering. We explore it for parametric spline geometry. By building on differentiable tessellation for Bezier V-spline and NURB surfaces, we can use your favorite differentiable mesh renderer. A set of regularization and coarse-to-fine techniques improves the robustness of image-based spline optimization. We show various applications in computer-aided design, including 3D object reconstruction and lens design. Visit our talk to learn more.
Thank you.
Have you wondered what could be the illumination for this indoor object? Well, I guess there are many possible solutions from the real-world distribution, and it's not deterministic. Traditional deterministic method can lead to unrealistic results. Our method proposes the diffusion, illumination prior, and ambiguity-aware inverse rendering that samples diverse, realistic material and illumination decompositions. The application of a method include material editing and relighting. Thank you.
Of constrained angles at vertices is a fundamental problem in geometry processing. However, for many angle prescriptions, a parametrization might not even exist for a fixed mesh. Retriangulation is often necessary. We describe how edge length coordinates or parametrizations of a given mesh can be extended to Penner coordinates for parametrizations of the surface with dynamic triangulation. By defining smooth geometric distortion measures and the angle constraints in this Penner coordinate space, we're able to formulate constrained optimization problems with guaranteed solutions. We also describe a method to find these optimal parametrizations using reliable numerical methods, achieving orders of magnitude less distortion than state-of-the-art conformal methods.
Cone singularities are introduced to reduce the area distortion. But how to efficiently construct sparse cone singularities? It is a challenging task. We combine the greedy and the optimization-based methods by making full use of their advantages. Welcome to our talk. Thank you.
Typical geodesic algorithms traverse O(n) vertices. This is uneconomic when we have many pairs of points to query. We propose a new algorithm, which achieves O(1) query time after pre-computation. Specifically, we extract vertex-wise feature and feed them in an MLP which decode the features into an output geodesic distance answer. Our pipeline could be easily migrated to other distance metrics, for example the harmonic distances, and it could handle corrupted unconnected meshes, which traditional algorithms can hardly solve. Thank you and welcome to our presentation.
Thank you.
We propose a novel approach for zero-shot 3D shape correspondence between strongly non-isometric shapes. We introduce a new benchmark as well as new evaluation metrics. Our proposed approach has three main components. First, we do zero-shot 3D shape classification using Flip2 and ChatGPT. Second, we do semantic region and mapping generation, leveraging the in-context learning capabilities of ChatGPT. Finally, our proposed SAM3D is used for semantic segmentation, and the segmented regions are matched according to the proposed mapping. Here are some qualitative results. Thanks for watching. See you this Thursday in the morning.
Hi, I'm Nima, describing how we simplify a 3D mesh with 14 million vertices in 1.3 seconds to one in which 7 million vertices have been removed via clustering. The state-of-the-art vertex clustering algorithm, as in Open3D, only parallelizes pre-processing, the spin code, but actual clustering is sequential. This fundamentally limits speedup to the pink region in this parallel speedup chart, but ours is over 7x. We do this by computing a dependency graph and processing it with atomic increments and CAS loops. On more than 70% of 400 large meshes from Thingy 10K, our parallelized clustering achieves speedups over 20x on 32 cores, which you can try yourself. Thanks.
Black and white photos whisper stories of the past. With the right words, we've given those whispers a vibrant voice. Using diffusion techniques, we develop a method to colorize black and white images where text serves as the bridge between text and user control and automation. And just like that, with a few text cues, we've shifted from grayscale to vibrant hues. Come see our talk on Thursday. Thank you.
We generate a 360-degree view of a person with a consistent high-resolution appearance from a single image. Existing 3D human generation approaches from a single image lack photorealism. Initially, we infer the 3D geometry in the back view, which we add with the input image to our support sets. For every new view, we aggregate the views in the support set and hallucinate the unseen appearance using a pre-trained entice diffusion model guided by shape cues. We finally use the support set to optimize UV texture map by minimizing the reconstruction loss between the rendered views and our synthesized views. Our results show consistent photorealistic 360-degree generations that are consistent with the input images.
Diffusion models have grown significantly in popularity recently due to their ability to generate diverse and high-quality images, but they are still not on the level of real images in all aspects. For example, real images, like the one on the left, must follow the rules of perspective projection, but there are no such constraints on images from diffusion models, leading to issues like inconsistent vanishing points and curvy vanishing lines. We attempt to solve this problem through the introduction of a physics-based constraint which aligns the image gradients of a generated image with its expected vanishing points. We find that this helps our model create images that are both more visually appealing and can serve as high-quality synthetic data for downstream tasks. Come by our presentation on Thursday at 12 or check out the website to see more.
In Monte Carlo rendering, point patterns can be hard to produce. Methods typically minimize energies with thousands of gradient descent steps, which can be slow. We instead train a diffusion network to synthesize new examples. The denoiser is a simple convolutional neural network, and the point structure is a problem. Using optimal transport, we impose a canonical indexing of points to a grid. This mapping allows to run efficient convolutions on them. With this mapping, a single network can be fast at generating high-quality samples. To learn more, come to our talk.
Thank you.
Diffusion models have garnered attention due to their impressive performance in image synthesis and restoration tasks. However, they usually cannot realize stable restoration and require extensive computational resources. In this paper, we propose a wavelet-based diffusion framework to achieve robust and efficient low-light image enhancement by leveraging advantages of wavelet transformation and generative ability of diffusion models. Our method effectively improves global and local contrast, producing visually satisfactory results in all cases.
Given an empty street view image, we build a system that makes it alive. The system consists of 3 stages. In the reconstruction stage, we reconstruct the basic scene properties in a game engine. In the simulation stage, we simulate pedestrian and vehicle movements in the scene. In the rendering stage, we render the street scene video with realistic shadow and occlusions. Here are some of our results. We are able to simulate the interaction between cars and pedestrians. We also work with panorama scenes. Come to our talk on Thursday for more details. Thank you.
Rivers are important landforms that shape the terrain and exhibit very different trajectory patterns. In our paper, we focus on the meandering stage, where the channel evolves into sinuous patterns due to erosion. More specifically, we simulate the evolution of the river channel using the migration equation, which creates these highly hypnotic patterns that you see here. We also show how to combine our simulation with vegetation and sediment to enhance virtual scenes even more. For more details, please come to our session on Thursday. Thank you.
Most people enjoy playing sand at the beach, where simulating scenario in real time can be very challenging. We introduce a framework to simulate water, sand, and mixtures in real time based on shallow water assumption. The sand behavior based on saturation level. And we demonstrate several scenarios simulated in our system in real time.
And immediately go to work. But what is that? The animation looks terrible because plant wilting is a complex process that is hard to animate by hand? Worry not! We studied the physics of water transport and evaporation for you and poured the results into a simulation framework. When comparing against real wilting plants, we achieved certified visual plausibility. Our simulator is integrated into Blender and is ready for you to be tested. See us in the simulation session on Thursday morning.
I have a moving least squares. I have a material point method. Boom, MLSMPM. I have a MLSMPM. I have a power weights. Boom. Power plastics. For more information, please come to our session.
Many recent methods encode 3D shapes into a learned latent space, generative design. Yet, it lacks effective mechanisms to explore the rich information in the latent space via a controlled manner. In this work, we propose to couple the clip and shape latent spaces for shape space exploration, demonstrating new capabilities beyond existing works. Here are more results on binary attribute guided exploration. Our explored shapes are produced to match the binary conditions. By leveraging the power of clip, we can achieve text-guided exploration without paired text-shaped dataset. Besides, our framework enables sketch-guided exploration. See the engines added to the airplane. For more details, please come to our talk.
Do you have a deep generative model that outputs 3D shapes? Come to our talk to find out how you can transform it into an intuitive 2D exploration space that produces smooth blends between shapes and preserves your original high-quality meshes. Our method facilitates shape-to-shape deformation, as well as continuous freeform exploration of large shape collections. Our method can be extended to generative models beyond 3D shapes, too. Please come to our talk on Thursday to find out more.
Thinking of new original ideas can be quite challenging. Designers often draw inspiration from existing visual examples. Extracting specific aspects of a concept is crucial for generating original ideas. Can computers assist humans in such a highly creative process? We present a method to decompose a given visual concept into different aspects, providing numerous image instances of each learned aspect. The learned aspects can be used to explore new design ideas. One can also explore compositions across different concepts.
Thank you.
We study deformable shape generators from a Riemannian geometry perspective by designing an extrinsic Riemannian matrix based on LAP and ACAP deformation pairs. Using this metric, we regularize the shape generator and perform latent shape space design with two desired properties. The first property ensures that linear interpolations follows geodesic curves, and the second property promotes pulse and shape disentanglement at multiple scales. Thank you.
CAD models are hard to manipulate. Identifying which parameters to modify can be challenging, and oftentimes, things break. Introducing ReParamCAD, a zero-shot pipeline that leverages large language and image models to infer meaningful space of variations. Given an input CAD model and a text description, we first generate a number of text prompts describing variations. We then use stable diffusion and differentiable rendering to modify the CAD model to match the prompt. We use a symbolic reasoning approach that discovers constraints that are common to all variations and expose meaningful parameters to the user. Come to our talk to learn more. Thursday morning, thank you.
Introducing NETI, a new neural representation for text-to-image personalization. Building on the time-dependent nature of the denoising process, NETI is conditioned on both time and space when encoding a new concept. Each combination of time and space learns to capture different aspects of the personalized concept. Earlier time steps focus on general structure and colors, while later time steps tend to learn finer-level style and texture. And rather than optimizing embeddings like contextual inversion, concepts are learned via a small network, giving us more flexibility. Find out more in our paper.
Thank you.
Let's perform some magics. Wow, my teeth don't feel good. If this were true, I would be rich. That's pointillism. This looks like a painting by Paul Cézanne. Steamed cake? I've never tried that. A spoon. Now I can enjoy the cake. These are all achieved by our method prompt spectrum from a single image input without fine-tuning the diffusion models.
Thank you.
Given a few images of an individual, Nizam and colleagues show that a personalized latent subspace can be obtained through tuning a pre-trained generator. However, they didn't demonstrate the precise control of the attributes of the generated images. To solve this issue, we propose a novel method that tunes the generator and organizes the latent space. The organized latent space allows synthesis images with great control of the attributes. Join us in our session on Thursday afternoon. Thank you.
There's been an explosion of pre-trained generative models. But how can users find their perfect model? To do this, we created a method and a web-based platform where users can search models with an image or a sketch or by typing some simple words. Please visit our talk Thursday afternoon. Thank you.
Do you want a beautiful drawing of your dog? Or a photo of it fishing? No worries, we got you covered. We propose an adapter for text-to-image models, which allows you to do all of that, and many more. All in a fast and efficient way. Oh, did I say that our method is also domain agnostic? Come to our presentation to learn more.
We introduced double cover UDF to robustly extract zero-level set from unsigned distant field, suitable for both closed and open models. Taking advantage of double covering, we formulated the mesh extraction as an optimization-centric problem. The resulting mesh exhibits visual appeal, characterized by the absence of non-manifold vertices, thereby ensuring topological cleanliness. Moreover, quantitative evaluation highlights the superior robustness and capability of our method. Come to our talk for more details. Thank you.
We consider the problem of reconstructing a surface from a signed distance field sampled at a finite set of points like a grid. Existing methods like marching cubes or dual contouring effectively ignore most SDF data and use local information to reproduce their reconstruction. We propose using all the global information, which we interpret as a set of spheres that the surface must be tangent to. Consider a coarse SDF of this shape. Here's marching cubes. Here's a recent data-driven approach, and here's ours. Don't settle. Reach for the spheres. A year ago in Korea, I presented an algorithm to go from a point cloud to a stochastic surface that incorporated reconstruction uncertainty. We had to use a finite element discretization and many other approximations. Today, we propose using a neural PDE solver, which has many advantages. It's differentiable, which means we can use gradient descent to find the next best scanning position. We can pre-train it on an initial scan of an object and then fine-tune it to efficiently update the reconstruction if we capture more data. And we can even generalize to a latent space of scans. Come to our talks to know more.
Let's suppose that you obtained a high-quality image from a generative model or from the internet. If you want to turn your 2D image into a 3D model, Pop3D can easily do that for you. Unlike previous methods, Pop3D can generalize across arbitrary in-the-wild images and produce state-of-the-art quality reconstructions. If you're interested, please visit us on Thursday afternoon. Thank you.
We propose MIPS Fusion, a neural RGBD SLAM method based on multi-implicit submap representation, which enables scalable online tracking and mapping for large indoor scenes. Based on divide and conquer mapping scheme, each submap is assigned to learn a sub-area of the scene, as shown by the colored bounding box, and a new submap will be created when scanning a new area. This incremental strategy ensures our method has the ability to reconstruct large scenes. Besides, our method can also handle fast camera motion. Here are the results of our methods under fast scanning camera motions in large-scale scenes. Thank you.
Generating useful contact point samples and normals for collision detection and resolution is not easy. By framing collisions as a surface integral over model boundaries, we can entirely sidestep issues of contact point sampling. Our integral formulation is not easily solved. Therefore, we store collision integrals as a neural network for query at runtime. Our collision solution is easily integrated into any solver supporting neural network evaluation. We demonstrate our neural collision integral as a constraint in position-based dynamics. We handle collisions in large scenes with thin and sharp contacts and with self-collisions. Come hear more at our full presentation.
The modeling of contact deformations can improve the realism of our interactions in virtual environments, providing visual feedback and haptic information. As shown in recent works, an efficient approach is learning deformations on top of reduced simulation models, obtaining rich contact detail. However, in these methods, the training just works for specific collider shapes, with a limited applicability. In this new paper, we leave these ideas to support general collider shapes, presenting, as far as we know, the first neural deformation model that generalizes to arbitrary collider geometries. If you want to know more details, come to our session. Thanks.
People come in all shape and size, and the pose they can adopt is equally diverse. Moreover, the world is filled with countless styles and sizes of clothing. Talking about clothing, we don't wear just one piece of clothing, we layer multiple pieces together. These factors make 3D virtual fitting a complicated and challenging task. Recently, methods for draping clothes on various body shape and pose have been proposed. However, most require a separate simulation model for each garment or do not allow for layering multiple pieces. Our proposed clothes combo offers a general method for draping clothes on diverse bodies in multiple layers. For details, please come to our presentation.
Thank you.
We proposed a novel, neural-based reduced-order framework for elastoplastic and fracture simulations. We achieved dimension reduction by up to 100,000 times, and time savings by up to 10 times. The key idea is to train 3 separate neural networks, neural deformation, stress, and neural affine field, so that these kinematic information can be retrieved at arbitrary locations. At each time step, we can perform a much cheaper, reduced MPM time stepping, to advance in the latent space. Our framework supports a variety of different fracture and elastoplastic behaviors. And the error is visually almost negligible.
Fluid direction is often based on the idea of time traveling into the past and interpolating from previous values. But doing so repeatedly introduces numerical diffusion, which is a big enemy to simulation accuracy. An idea to counter this is to travel further back in time and fuse multiple interpolations into a single one. However, computing such a long-range time travel is not accurate without knowing the long buffer of historical states, and for traditional schemes, this is considered intractable. To this end, we harness implicit neural representations as a new type of data primitive for simulation. Replacing a grid with our novel neural structure, we move from storing a single frame to a long history buffer, which unlocks the opportunity to design a new algorithm that drastically improves the simulation accuracy. Come to our talk.
Tracking has wide applications in XR devices. However, current methods suffer from various limitations. For instance, visual hand pose estimation is susceptible to self-occlusion and changes in lighting conditions. And IMU-based tracking gloves experience significant drift and are not resistant to external magnetic field interference. Here we propose a novel glove that utilizes MEMS ultrasonic sensors attached to the fingers to measure the distance matrix among the sensors. Our lightweight model then reconstructs the hand pose from this distance matrix. We show you demo results. It demonstrates that this approach is both accurate, size agnostic, and robust to external interference.
Computer graphics and virtual reality rely on visual feedback, but what if you cannot see? We introduced Shape Sonic, which provides a way to perceive shapes with sonification or sound feedback from the user's hands. We sonify contact, sharp features, and the shape around the space around the shape. We ran experiments with sighted and BVI users. They were able to successfully recognize shapes and relocate landmarks on them, like on a cat. Here is an example. Come see my talk and find out what this shape is.
To generate realistic audio in apps, many developers use GA-based sound rendering. However, several limitations making it challenging to use in apps. To address these issues, we designed and implemented a sound propagation hardware. We incorporate on-the-fly algorithms and modified propagation algorithms parallelly. Furthermore, we achieved a low power consumption and a small die size.
The egocentric setup utilizes HMD cameras without any external device for accessible VR and AR applications. We propose a highly accurate binocular egocentric pose estimation method. Egocentric setup struggles from the lack of the visual cues due to self-occlusion, and existing methods struggle despite of the sufficient stereo-visual cues. 3D pose estimator overfits a common correlation between joint neglecting stereo views. We extract 3D visual cues from images with our trigonometric representation and add a new path for extracting features focused on stereo pairs. Joe now talks for details. Thank you.
We introduce an active 3D reconstruction method. Given an object, the robot first moves in front of it and obtains the point cloud scan. The action is then chosen from the predicted interactability map. The robot then rescans the object to obtain the point cloud in its current state. The moving part is then reconstructed and the next action is selected from the updated interactability map. The same scanning and reconstruction processes are executed for another part. If the stop condition is reached, we merge the parts to form the final result. Want to know more? Come to our talk on Thursday.
Thank you.
When we use the robot to scan the unknown indoor scene, which kind of results is more friendly to rendering, to editing, and to interacting with? As we all know, it's the most widely used representations are the point cloud and the mesh. But can your application tolerate with the noise in these applications? Now we introduce the online CAD recomposition method to scan the scene autonomously and generate a clean result. It's so easy to edit our result, and all changes can be finished immediately without introducing any geometric errors. Want to know more? Come to see our talk. Thank you.
Given a scene, a human agent, and an activity description, our goal is to generate a scene-aware program to instruct a human agent to accomplish the desired activity. We propose a novel method for program generation, where the scene is represented as a scene graph. Our key contribution is utilizing the language rationality of a pre-trained language model to create highly rational and executable programs. As shown in the following activity demonstrations, the generated activity program can serve as intermediate states to greatly facilitate the creation of fairly complex and long-lasting animations.
Thank you.
I can show you the rod, bending, twisting, and stretching. Oh, geometry, how do I invert a Kirchhoff rod?
A new project in point of view, design it and observe the pretty curve that our math predicted.
That's what you'll see.
You come see
my thrilling talk
at 3 o'clock
for you and me.
To model personalized avatars, spending hours and hours training their soft tissue parameters from mockup or skin deformations? Now you can use Splash, a new soft tissue model that generalizes to arbitrary body shapes. With Splash, make your avatar work out much faster and have interactions. Sign up your avatar for fitness classes with other avatars, each with their own personalized soft tissue deformations. Put your avatar in shape with Splash. No avatar has been forced to perform any exercise against their will for this video.
Thank you.
The simple body model is good at representing the human body shape.
But the kinematic tree does not look anything like a human body.
In our work, we learn scale, a body model representing the skin with the anatomical realistic skeleton inside. Scale has a shape space and realistic human joints like a spine, knees, shoulders, elbow, and forearm.
Compared to simple, our model provides an anatomical human correct and joints. It has less degrees of freedom, which are also meaningful.
Enabling an avatar with multiple skills has been challenging, let alone teaching new skills. The good news is that the neural motion graph is here to tackle these challenges. To be more specific, our graph employs a deep neural network at each graph node to model a specific type of motion. All transition edges between these neural nodes are designed to be handled by a single network. Multi-skill, integrating new skills, and even different control for different skills. Welcome to our talk. Thank you.
We propose a novel method to recover FAVR data from a single flash image. We use a correlation between different pixels to fill in the gaps. SVBRDF can be expressed as a mix of physics BRDFs and weights. We introduce them into the prediction of deep learning. And the final SVBRDF is their linear combination. Come to our talk and find out more.
Thank you.
Do your SVBRDFs have artifacts? Are your normal maps sad and flat? Did you get the wrong roughness or specular reflectance in which you could just generate a different solution? We have a fix for you. With Map Fusion, you can randomly sample the distribution of SVBRDFs. And another special offer, you can fine-tune Map Fusion on the lighting of your choice. Lit by flashlight only, by an uncontrolled natural environment, or by both at once. Best of all, you don't need a differentiable renderer to fine-tune. The possibilities are endless. And since Map Fusion is a diffusion model, you can be sure your graphics paper contains all the best buzzwords. Please come to our talk to learn more or download Map Fusion and our fine-tuned models online.
Textures represent surface appearance and consist of repeating patterns. Numerous applications use textures. A user can modify an image appearance to that of a texture. Sometimes users can easily obtain holistic textures that are rectangular and undistorted, but it's not easy to obtain a holistic texture from most real images. This is caused by perspective issues, distortions, and occlusions in real images. Our framework allows users to simply select the desired region and rectify the distortions and occlusions. Thank you.
Many applications need reflectance databases for training. However, to acquire a large-scale dataset remains challenging due to technical limitations. We propose a novel integrated system, with acquisition setup and special neural processing, for robust, high-quality and efficiency capture of near-planar reflectance. Using our system, we build the first large-scale database of measured spatially varying anisotropic reflectance, consisting of 1,000 high-quality near-planar SVBRDFs, spanning 9 categories. All related data can be freely downloaded from this website. Please come to our talk for more details about our approach, as well as applications.
Thank you.